All right, this is the second in what is likely to be 3 videos on this little mini series on calculating network values using linear algebra, or alternatively, finding out methods for obtaining these loop currents and then using Wolfram alpha to have these answers spit out. All right, so here is this top portion, the circuit we're going to use today. And this one is only slightly more difficult than part one, or the first video in this series. But because this does involve some visual trickery, I thought I would throw this in here before I move on to the third video at some point in the future, where I'm going to add an extra power supply in there. So for my electrical 1 and 2 students, you will never see a second or third or fourth power supply added into a circuit. It's just not the path that those courses are on. So that third video in the series, once or if I end up making it, will really show the limitations of how we show you how to do it in electrical 1 and 2. And again, it's not because we don't know the limitations. We don't know how to do it. It's just it's not the path you're on. So we make things as simple in that regard as we can here for you. So you can obviously tell there's more loads in this circuit. Ultimately, there's going to be more branch circuits, more loops. But the visual stunner right here is this R3. We've got this crazy thing down here on a diagonal. Now, we do what I would call you dirty here a few times during the electrical 1 and 2 course by throwing in something that is not parallel and perpendicular. Now, I do this right from pretty much the get-go in electrical 1. And I do it just to get you used to the fact that you should not be afraid of anything like this. These things are as simple as they can get. The point I show to you is take this conductor here on R3, this end of R3. You can move it anywhere you want. Don't go past a point. In this case, you could go past a point, but it would confuse the numbering convention, and you could do it, and as long as you kept track of everything, it would be fine. But for simplicity's sake, don't go past a point and never go past a control. Now, we don't have any controls, switches, push buttons, etc. You can't do that either. So with those easy restrictions to remember, just you can move this conductor here on R3 anywhere you want around here, and you can do the same thing here. And your goal is to make it parallel or perpendicular to the rest of the loads in the circuit. So you can very easily redraw this into this. All I've done is straighten up R3. And once you have it visually in this configuration, you recognize this as just something you've done 1,000 times over. All right, so there again, I always have you set up the table. And I'm not going to go through our usual method of calculating all this because it's just ad nauseum at this point. You already understand. Set it up on the table so you know the values that you're missing that you need to get. And this also tells you in what order you need to do it. So as is almost always the case in electrical 1, electrical 2, we give you all the resistances. The only oddball is sometimes we throw out a resistance, but we have to give you something else to make it solvable. It's usually a current somewhere. But in this case, you know you would just find RT, total resistance. And once you've got that, then you can calculate current because you have the circuit source voltage, 18 volts in this case. And once you have the current, you have to look back at the circuit. This is IT, total current, and recognize that I1 and I6 are going to be the same as IT. So then you calculate the voltages off of that. So you have V1, V6, and you recognize that VT minus V1 minus V6 is the voltage left over for the rest of the circuit. Now the rest of the circuit is effectively just a parallel circuit. R2 in parallel with R3, one wrinkle, sum R4 and 5 together. So that would be 300. And that is what's in parallel with R2 and R3. So you get the voltage here. So now you have V1, V2, V3, V6. And whatever V2 and V3 is, the sum of V4 and V5 are going to equal that. And once you have the voltages here, and you already know the currents, you have a current going through here, you use Kirchhoff's current law. So the total current, which is also I1, also ends up being I6. this amount of current minus I2, which you can calculate, minus I3, which you can calculate, will give you the current in this branch. And once you have the current in this branch and you have the resistances, you can then calculate the voltages, V4 and V5. And remember, V4 plus V5 must equal V2, which will also equal V3. That's how you do it, right? So enough with that, because we don't want to make this video any longer than it needs to be. Once you've got this, let's take a look at this new methodology that I've been showing you in the previous video and we discussed very briefly in class. It's the same story. You choose an arbitrary direction and recognize there are 3 branches in this circuit. So you're going to have 3 branches, 3 loops, you're going to have 3 equations. It's just more of the same. The resistances of in this IA loop times this current will eventually give us the voltage over here. That's what we're going for. But if you'll notice that the current in branch, this R2 branch is going the opposite way. So it would be minus 300 times IB. And IC isn't in IA, sorry. So we just don't use it. You do the same thing with IB. Now IB is interesting because the current in this loop contains R2 and R3, and those 2 resistance values are those specially treated ones because they are also in branch IA and branch IC. And you'll notice I'm not keeping them in order. I'm just writing them down with the first term, whatever branch they are in. So IA, IB, IC. Okay? And once you get those equations, run over to Wolfram Alpha, pop them in there, and just replace IA, IB, and IC where appropriate for X, Y, and Z. And you're good to go. Now, the linear algebra way of doing it is, remember, in the columns, you have to keep all your IAs, IBs, and ICs in their appropriate column. So in this first column, there's no IC, you just put a 0 in. In this second loop here, it's going to contain elements from IA and IC, so there won't be any zeros there, and IC doesn't have an IA group, right? And what we're doing here is just R times I, we're going to find the I's, equal V. In this case, the only power supply is found in the branch IA. Augment the matrix, do your reduced row echelon form, and if you come out to something that looks like that, the identity matrix, you've done it right, and what immediately pops out are your answers, IA, IB, and IC. These 3 numbers are what you get when you pop in these 3 equations into Wolfram Alpha. And the only thing left to do, the only thing that I'm going to show you here is, now that you have these branch currents, remember I2 and I3, or resistors R2 and R3, are treated somewhat differently because they contain currents, and in this case, going in the opposite direction of their other 2 branches, and you can see that because there's negatives here. And again, this is arbitrary. You can come up with the same answers using a different matrix if you just happen to choose a direction going the other way, but it would still always come out in the wash to the final correct answer. And the final correct answer, as far as currents go that we don't yet have, we have to find the current through I2 or R2 and R3. The currents there are just going to be, because they are opposite, I2 equals IA minus IB will give you this current. And remember, that's in amps because these are all base units. Resistance in ohms and voltages are just in volts. So base units. And the current through I3 is IB minus IC is this right here. So I won't spend any more time filling all of this in because you pretty much have the answers, and the rest is simply adding and subtracting. So very, very quickly, I'll just go through it, but I won't write it all in. You know what IT is. IT is IA. So you'll have IT, I6, and I1 all as the values for IA. I4 and I5 you already know, that's IC. So the only thing that you need to need to do to find I2 and I3, you've just done here. So now you have all your currents. You just do V equals I times R. You've got all your voltages. Remember to pay attention and just have a double take. If you've made any mistakes, you know that V2 and V3 will be 18 volts, VT minus V1 minus V6. So make sure that that works out, and make sure V4 plus V5 also works out to these same voltages. It's just a good double check to make sure that you haven't done anything wrong. And from there, you can find RT. It's just VT divided by IT.